everybody. I'm very happy to introduce our speaker. She is Carina Curto from Penn State University. She's a professor at Penn State University, and she's one of the heads of the Mathematical Neuroscience Lab at the math department there. And if you would like to read something nice about her, I just put on the chat a link to an interview with her at Quanta magazine. And I'm very happy to leave you with Carina. The title is there. Please.
Thank you. Thanks, Alicia, for inviting me to this seminar series. And I've come to several of these actually, so I'm happy to finally speak myself also. So I'm gonna talk to you today about some work that we've been doing with neural network dynamics for neuroscience applications. So you can see the title, Dynamically Relevant Motifs in Inhibition-Dominated Networks. So this is really a mathematical neuroscience talk, although I think the flavor has some insight from the geometry of hyperplane arrangements and also some, graph theoretic insights as well. So hopefully it will be of interest to this audience. Okay, so I want to begin by thanking my students, postdocs, collaborators. First and foremost, Katie Morrison up here at the top left. Can you guys see my cursor, by the way, on Blue Jeans?
Yes, we
you
can.
Okay. Okay, great. So Katie is my long-term collaborator. Basically, everything I'm going to talk about today, she has had a heavy hand in. So just keep that in mind. And also Caitlin Parmalee, former student of mine, as well as Juliana Londono Alvarez. When I talk about the Quadruped Gates at the end, that is primarily her work. And then I also want to thank other students and postdocs, Josh Pike, Caitlin Leinkamper, and then Chris and Jesse are former postdocs with my group, and Nikki Sanderson is a current postdoc in my group. And then also a lot of this work was jump-started by a previous collaboration that I had with Vladimir Itzkov and Anda Degeratu. And I also have some other collaborators that have done related work with me. So I'd like to acknowledge all of them. Okay, let's get started. So the starting point in terms of the neuroscience that I think about is really the classical Hopfield model. So many of you are probably familiar with this model. Basically, anybody who's done computational or theoretical neuroscience learns this early on. And it is a prototypical model of attractor neural networks for memory encoding and computation in the brain. And so the idea is that you have networks of neurons, and every neuron has a state. In the case of the classical Hopfield model from the 80s, the state is typically on or off, so the neuron's either firing or not firing, and it's denoted by this SI of t. And there's an update rule, which basically signifies the influence of other neurons in the network on the neuron in question. So the sum Wij Sj is showing the influence of the recurrent interactions on the state of Sj, and then comparing to some threshold in order to update the state. So there's a very famous result from the early 80s that this is sort of the reason that the Hopfield model is called the Hopfield model, although of course many other people worked on it before and after. And what Hopfield was able to do was write down an energy function, or a Lyapunov function, if you will, that decreases along trajectories. And so with this, he was able to show that no matter what initial conditions you have for this network, the activity is guaranteed to converge to a fixed point attractor. Okay, now, 2 important points. These are static attractors, and I will make the distinction between static and dynamic attractors later in this talk. But essentially, the attractor state really is just neurons that are firing and keep firing at a steady state or an equilibrium point of the dynamics. Second important point is that he was able to prove this for symmetric interaction matrix. So in other words, this W matrix, which is governing the interactions between pairs of neurons, needs to be symmetric in order for this energy function proof to work. Okay, so I don't actually study Hopfield networks per se. The networks that I'm going to talk to you about are kind of a more modern version, which are called threshold linear networks. So these networks are very popular in computational and theoretical neuroscience. So they, maybe hundreds of papers use these equations to model network dynamics in various applications. And the idea is quite simple. So again, you have a bunch of neurons connected in a network. There is a variable for the firing rate of each neuron. So xi of t is the firing rate over time for neuron I. And there are these simple threshold linear dynamics where in the absence of recurrent or external input, the neuron decays to rest with some time scale that's been set to 1. And when there are other neurons influencing it inside this term, then provided this term is above 0, you get a boost to the firing rate. So there's some increase in the derivative that can happen when this term is large enough. And so the brackets with the plus is really just denoting the max function between the argument inside and 0. And so here is a little plot of the function. In machine learning, this is called ReLU nonlinearity, but we call it a threshold linear transfer function. And this matrix, the threshold linear network with matrix W and this external input vector B, we can refer to by the ordered pair WB. So that is all the data that goes into defining these networks. So perhaps surprisingly, these very simple equations can lead to all kinds of interesting nonlinear dynamics. And why do I say this is surprising? Because if you look at these equations and you pick a generic point in the state space, so generic x1 through xn, you will either be on the plus or the minus side of this nonlinearity. And when you're on the plus side, you can drop the brackets because you get identity function. And when you're on the minus side, you just set it to 0. So locally, every equation collapses to a completely linear equation. And so you have a linear system of ODEs. And so this is really a piecewise linear dynamical system. And the surprising thing, perhaps, is that despite the local linearity of it, in the patching together of all these different linear systems, you actually get the full variety and richness of nonlinear dynamics, including multi-stability, like in the Hopfield model, but also limit cycles, chaotic attractors, and even quasi-periodic attractors all emerge in these networks. And in particular, they can emerge for constant B, constant in time and constant across neurons. So it's not just an external input that's driving the interesting dynamics, but also it's really intrinsically generated. But they can also arise for an effectively inhibitory W. And that is the case that I'm going to focus on, as suggested in my title, is the inhibition-dominated case. So there are some older results about these networks that I should acknowledge. So first of all, about 20 years ago, I would say that this is where the kind of mathematical theory really started taking off with the work of Sebastian Sung, Hallnazor, Slotine, and others. And they wrote some lovely papers proving some basic theorems about these networks in the symmetric case. So again, like with the Hopfield model, they first focused on the symmetric case, and they cared about stable fixed points of the dynamics. And so they developed this nice theory of permitted and forbidden sets in the symmetric threshold linear networks. And in particular, they proved a result that's analogous to the famous Hopfield model result, where they showed that if W is symmetric and if the network is inhibition-dominated, so non-positive W matrix, then they could also write down an energy or Lyapunov-like function that was guaranteed to decrease along trajectories and therefore guaranteed that the network dynamics would fall into one of these static attractors. Okay. This, of course, again, like in the Hopfield model, is meant to be a model of associative memory encoding. So the idea is that some stimulus comes, it puts you somewhere in the state space. The external input puts you somewhere in the state space in this model, and then the dynamics evolve into an attractor. So something like, I smell oranges, and then I think of my grandmother, right? So these are kind of associations that would be embedded in the network in the recurrent weights. Okay, so they showed these networks are at least as good as the Hopfield model in some sense in order to demonstrate attractor-like dynamics. But later, together with Anna Digerato, Vladimir Itzkov, and also Katie Morrison, we wrote a series of additional papers that I actually think are mathematically quite interesting, looking again at the symmetric case and what are the full collections of neural codes that can be encoded in these networks. So here there's actually some some nice, in this paper in particular, the 2013 one, there's actually some nice connections to distance geometry, the elliptope, if you know what that is, and other connections to sort of convex optimization and so on. But I'm not going to talk about that today because that's like old work. And what we've cared about in the last 5-6 years is really quite complementary, because now we are focusing on non-symmetric W. So I really want to get away from that symmetry assumption, because basically, even though we know these networks can produce this sort of full range of nonlinear dynamics, in the symmetric case, you really are confined to static attractors, like in the Hopfield model. And you really have to go to asymmetric connectivity in order to access the other kinds of nonlinear dynamics. I should also say that the symmetric assumption is particularly unrealistic from a neuroscience perspective, even though it's been used over and over again for mathematical convenience. So the motivating question we have now is, what is the relationship between the attractors of a recurrent network and its underlying architecture? Same question that you might ask back in the Hopfield model, but now we care about dynamic attractors as well. We care about limit cycles and so on, and we want to know, can we predict those from the architecture of the network? And to what extent does the detailed pattern of connectivity of the network drive the different interesting patterns of neural dynamics that we can see? And so we are going to really focus on the structure of the network as encoded in a directed connectivity graph. And to do this, so first of all, let me show you an example of what I mean by these other kinds of attractors. So here's a small network, threshold linear network with just 9 nodes. There's a W matrix here. I will sort of explain later how I constructed it, but the point is it's closely tied to a directed graph. Okay, so when there's an edge in the graph, the W matrix has like a larger value, and when there's not an edge, it has a more negative value. And what we see in a simple network like this is that you have coexistence of many different attractors. In other words, there is not one asymptotic behavior of the network as you evolve the dynamics over time. It depends on initial conditions. So for some initial conditions, you will converge to one of these stable fixed points. So those are 2 attractors that are encoded in the network, and those are the traditional static attractors where the activity just goes to a constant firing rate for some subset of neurons, and the other neurons are off. Okay, so that is kind of the classical picture. But for other initial conditions, you may converge to a dynamic attractor, meaning a periodic or a quasi-periodic pattern of activity that continues evolving but is nevertheless confined to a very small sort of measure 0 subset of the state space. So, and this is what you see here. So how do you read these graphs, by the way? So the firing rate of every neuron, the xi of t, is given in the same color as the neuron on the graph. So for instance, blue is for neuron number 2, and here you see the dynamics x2 of t over time. And so what you see in this limit cycle is for certain initial conditions, you converge to a periodic solution where the neurons are firing in order 2, 6, 3. It actually follows the cycle in the graph. It's not obvious that it should do that, but it does. And you can see those are the high firing neurons, and there are some other neurons that are maybe activated a little bit, but these are the dominant ones in that particular attractor. We also have a chaotic attractor, chaotic in the sense of sensitivity to initial conditions. This pinching behavior appears to happen at random times and will vary considerably if the initial conditions change a little bit. But it's also in some sense highly regular, because you have here activity concentrated on just 3 neurons, and they are 3, 4, and 5. And you can see there's a 3 cycle in the graph as well that's corresponding to this attractor. So one of the things that we want to understand is, given one of these graphs, can we predict, who these attractors will be? Maybe we won't predict the fine details of the attractors, but we can at least predict these subsets of neurons that will support the attractors and whether they're stable fixed points or dynamic. Okay, so in order to study this question, again, we have relaxed from the symmetric case. We are now considering asymmetric networks, and so we need to impose, at least to begin with, some additional assumptions to make life easier. And this has led us to look at a special case, which is combinatorial threshold linear networks. So these are all threshold linear networks. What makes them combinatorial is that the W matrix really is completely dictated by a graph, by a directed graph together with a choice of epsilon and delta parameters.
Yeah.
Okay, so what makes this a special case is that we are, instead of looking at all possible W matrices, right, which is like kind of an n squared parameter space, we are focusing in on matrices that are parameterized by a directed graph and this epsilon and delta. So the epsilon and delta are just determining how much above or below -1 the entry is. And so really what is happening here, the way to think about it, is that when there's an edge between two neurons, you have a weaker inhibition, so something above -1. And when there's no edge, you have strong inhibition. So these really are inhibition-dominated networks. And the way we think about it is that there are excitatory connections between the neurons, but there's also the sea of inhibition. So these gray nodes here, which are not represented in the model officially, are representing kind of a sea of inhibition. You can actually include these and do a calculation to reduce the network to looking just at the excitatory nodes, and what it does is it shifts the effective weights between nodes downward. And so you can think of this -1 plus epsilon as a sum of an excitatory weight and this kind of background inhibition that's causing strong competition between all pairs. And then when there's no edge, you just have the strong inhibition. Okay, so you can think of these as some kind of generalized winner-take-all networks. So they're competitive networks. All the neurons are competing against each other. They don't like to co-fire. The firing of one is causing inhibition to the others, but some inhibition is stronger and some is weaker. Okay, and a particular note, the -1 is not some arbitrary choice. It's actually dictated by the self-leak. So remember I said we're measuring time scale. We're measuring time in units of this time scale that is dictating the time scale of the exponential leak back to rest when the neuron is not getting input. And so the weak inhibition means that the effect of neuron J on neuron I is less inhibitory than neuron J's self-inhibition through its self-leak. So when you have an edge in the graph, you have weaker inhibition than the neuron's self-inhibition. And when you don't have an edge, you have stronger inhibition than the neuron's self-inhibition. And so intuitively, you might think that the activity will want to move along the edges because those are the pathways where there's less inhibition. There's also this parameter theta that's driving everything from the outside. Theta needs to be positive or the whole network will die. And so for many of the results that I'll tell you about today, theta will be constant across neurons and in time. But of course, we also investigate varying theta and how that affects the dynamics and so on. Okay, so let's just look at some examples to see what kinds of dynamics we get for this setup. So one, interesting thing that you learn right away when you study these networks is that the dynamics are really shaped by the global structure of the graph. So in other words, you cannot predict the pattern of activity by looking just at the degree sequence. So this is a series of 4 graphs that all have matched degree sequence in the following sense. So every neuron has an in degree and an out degree. So here neuron 1 has in degree 1 and out degree 2. And if you put together all of those degree pairs, you get the degree sequence for the graph. And all 4 of these graphs have exactly the same degree sequence. And however, their dynamics are completely different. So the local properties of the network are not sufficient to determine what's going to happen. In the top network, you have a single limit cycle, and it involves neurons 2, 3, and 5 firing in a cycle. In the second graph, you have 2 limit cycles for neurons 2, 5, and 3, and also I think the other one is 1, 2, 5. At the bottom here, you have 3 stable fixed points are the attractors of that network. And at the right, we have, this is what we call baby chaos. It's a network with 4 chaotic attractors. So same degree sequence, same local properties. If I just, were given descriptions of the neurons and their in and out degree, the epsilon, delta, and so on, locally these networks are identical, but of course the global structure is different, and that makes all the difference with the dynamics. I should point out, by the way, that the embedding of these subnetworks that are supporting the attractors also matters. So for instance, if you look at this top graph A, you have this 3 cycle 2, 3, 5 that's corresponding to this attractor, but you also have another 3 cycle 1, 4, 5 that looks like it's embedded in very much the same way in this network. And yet this other 3 cycle does not have an attractor associated to it. So that, kind of thing was initially a mystery to us. I will show you later the resolution of that puzzle. But for now, you can just kind of try to figure out what is different about the embedding of 145 as compared to 235, because they really are not embedded in the same way, and that is why one of them has an attractor and the other does not. Okay, so we also have, a rich variety of dynamics in these networks beyond just like these 3 cycles. So I wanted to just flash a couple of examples of fun limit cycles. So here is a very symmetric graph. This is a circularly symmetric tournament, and it has, as you might expect, a limit cycle where the neurons fire in order around the edge of the graph. So 1, 2, 3, 4, 5. You track inside this limit cycle, the neurons are really just firing in the expected order. However, the exact same network, same W matrix, everything, all parameters the same, no change to the equations at all, except changing the initial conditions, I can get a completely different attractor, which is my favorite attractor. So I call it the Gaudí attractor because it reminds me of the architect in Barcelona, but it has these like melting curves that really come from a very different sequence around the graph. So in fact, if you track the peaks of these curves, you get activity that goes in along the other cycle. Okay. So I think this is quite lovely. You can also get quasi-periodic attractors where you can see that the trajectory in the state space traces out kind of this beautiful torus. So this is a network that also has 2 attractors, a very regular one that has this regular sequence that you would expect, and that is the red curve in this projection, and also the torus for the quasi-periodic attractor. Okay, so how do we analyze these networks? So I hope I've convinced you by now that they are a rich family of networks motivated by neuroscience, and then ones where we would want to understand the dynamics. And so the main strategy that we use is to really focus in on the fixed points, but not just the stable fixed points, also the unstable fixed points, because it turns out that the unstable fixed points are tightly related to the dynamic attractors in ways that are that we can understand. So the first observation is you can think of the threshold linear networks as a patchwork of linear systems, as I was saying before, that are where the boundaries between the linear systems are determined by hyperplanes that are coming from the equations. So in other words, every equation can be written in this way where you see immediately the switching is going to happen when y sub I equals 0. That's when you're going to switch from the positive to the minus side. And y sub I equals 0 is determining a hyperplane whose normal vector is given by the ith row, or in this case, first row of the W matrix, and then there's a shift given by the theta term. And for each neuron, you have one of these hyperplanes. So altogether, they form an arrangement of n hyperplanes in the positive orthant is really where we look at them, because the activity is guaranteed to stay non-negative if you start non-negative. And this chops up the positive orthant into these chambers, and inside each chamber you have a linear system. So there are a few observations that you can immediately make from thinking about this hyperplane arrangement picture, and one of them is that under some mild non-degeneracy conditions, each one of those linear systems can have only one fixed point, and that fixed point may or may not live inside the chamber where the linear system is governing the dynamics. And so, in fact, it ends up happening that you have a one-to-one correspondence between fixed points and allowed supports. So given a support of a fixed point, which is the neurons that are non-zero at that fixed point, you can actually, there can be at most one fixed point. So for each support, there can be at most one fixed point. So if I tell you, is there a fixed point where neurons 1, 3, and 7 are all firing and everyone else is silent? Well, you can check, but if there is one, there is at most one. And it really depends on whether the corresponding linear chamber contains its own fixed point for the linear system inside the chamber. And so once you have this perspective, you see that you can label the fixed points by the supports. And so the whole game of figuring out the fixed points of a network is figuring out who are the allowed supports. So here's an example of a fixed point and the limit cycle associated to it. So if I look at the network, a network that is generated from this 3-cycle graph, this is a very simple graph, you see here that you get a hyperplane arrangement with 3 hyperplanes, as expected. And of those 8 chambers, only one of those chambers contains the fixed point of the corresponding linear system, and that is this central chamber here. It's the chamber that contains the origin, in fact. And if you perturb around that fixed point, what's going to happen is you spiral out. It is an unstable fixed point, so there's a pair of complex conjugate eigenvalues with positive real part. So you spiral away from it, and then you cross into different chambers. And so you can see here the trajectory. It spirals out, crosses into a new chamber, and then it comes back into the central chamber, spirals out again, and so on. And you eventually settle into a perfect limit cycle where the reason it patches together is because every time you come to the central chamber, you sort of catch the spiral out at an earlier point than where you left it. And so this is how it can patch together. I should say there's a group of mathematicians from Argentina, Horacio Rothstein and collaborators, who were able to prove the existence of these limit cycles, not just for the 3-cycle, but also for multiple other trajectories. So they have a recent paper out in SciAds on this. There's also unstable fixed points kind of at the heart of the chaotic attractors. So you can see here in baby chaos, if I were to plot sort of the minimal unstable fixed points here, I would see a fixed point at the center of each one of these little hurricane-like pictures for the trajectories. So we care about the stable and the unstable fixed points, and the way that we are going to relate that now to the graphs is through these graph rules. Okay, so the whole kind of magic of these networks is that, first of all, the unstable fixed points are closely related to the dynamic attractors, and second of all, that we can understand what fixed points we're going to get through results that directly relate the fixed point structure to the graphs. And these are the so-called graph rules. So the graph rules are really theorems, but they tell you how to relate the graph properties to the fixed point structure. So my favorite graph rule that I like to tell people about is the uniform in degree one. So this one simply says if you have a subnetwork that has uniform in degree, so all nodes have the same number of incoming edges, uniform in degree D. So for instance, A3 is uniform in degree 2, A4 is uniform in degree 1. Then we have the following theorem, that the support of the subnetwork is a fixed point support in the full network if and only if there's no node outside the subnetwork that receives D plus 1 or more edges from the nodes in the subnetwork. Okay, so this is an if and only if statement. It tells us precisely when uniform in degree subgraphs will be supports of fixed points. And to illustrate sort of the power of this, as corollaries, you can look at special subgraphs of uniform in degree, like cycles. A cycle has uniform in degree 1, no matter how many nodes are in the cycle. It's every vertex gets 1 incoming edge, and such a cycle will have a fixed point associated to it that survives in the larger network if and only if no node outside of G receives 2 or more edges from G, right? So D equals 1, D plus 1 equals 2. And this immediately explains to us why we don't see a second attractor for this other 3-cycle in this graph. So this is the A graph that I showed you before. And what we see here, there are 2 3-cycles. Each of those 3 cycles in isolation has a fixed point associated to it and a limit cycle associated to it. However, once you embed it, you see that only the 2, 3, 5 3-cycle has a surviving fixed point, and that is because none of the nodes outside of 2, 3, 5 receives 2 or more edges from the nodes inside 2, 3, 5. However, the other 3-cycle, 1, 4, 5, does have an outside node, namely node 2, that is receiving too many edges from the nodes inside the support here. And that is sufficient to kill the three cycles fixed point, and then we also see that the attractor disappears. Okay. Similarly, when you have a click of size k, the fixed point for the click is going to survive if and only if no node outside receives k or more edges from G. So, this is an example of a graph rule. The uniform in degree one is the first one here. We also have a series of other graph rules, and this list is much longer by now, where we are directly relating properties of the graph to properties of the fixed points, right? To sort of describing the fixed points. And remember, if you go back to the hyperplane arrangement picture, it's complicated to figure out which fixed points are going to be there. And in some sense, the brute force mechanism would be to sort of check all these linear chambers from your hyperplane arrangement for each linear chamber, figure out the linear system, find the fixed point for that linear system, and then determine whether that fixed point is lying inside the chamber or not. You'd have to do all of that in order to figure out whether you have whether that support is a fixed point of the network. But with the graph rules, right, now somehow we have been able to tie this all the way back to the original structure of the graph. Of course, the graph is determining the W matrix and is determining the chambers of your hyperplane arrangement. But the beauty is relating the fixed point structure directly to the graph. So we've been able to do that. And one of the things that we've been looking at recently is trying to pull back the graph rules to a sort of an elementary set of graph rules. So the idea here is that we can prove many sort of auxiliary graph rules or derived graph rules from a set of elementary ones. And so what we would like to do is kind of axiomatize, find some basic set of graph rules from which the other ones will follow. And one of the things that is nice that we've discovered is nice about that is that certain graph rules that are related to what we call a simply embedded structure of subgraphs allow us to take fixed points from subnetworks and kind of glue them together into fixed points for the larger network. So we have, in some sense, like a pre-sheaf and a sheaf-like structure. So let me just quickly review some of the elementary graph rules we find. So these are the really basic ones where we go back and prove them directly from the threshold linear network equations, but then we can use these to obtain derived graph rules. So any network, any neural network system that would from which we can prove these basic graph rules would then have the derived ones. And so I've already talked about uniform in degree. Parity is a very nice one. The total number of fixed points of these networks is always odd. Okay, and that is actually coming from the Poincare-Hopf theorem applied to these networks. So we have like an index theorem that is going to give us this result on parity. And we also have a graph rule of domination. So this is a particularly interesting one, which tells you that if you have two neurons where one dominates the other, meaning it's receiving all the inputs that the other one is receiving, then you actually have some situations where you're forbidden. What?
What is FP of G?
Yeah, FP of G is the collection of fixed point supports. So this is the collection of sigmas that support fixed points. So it was defined on a previous slide. I apologize for not reminding what it is. So anyway, once you know FP of G, you know all the fixed points of the network. Okay, so this really is the collection of all the fixed points. So anyway, it takes some time to sort of explain all these rules in detail. I've explained the uniform in degree one in some detail, but one of the things that so maybe there's a family of graph rules that I want to tell you about, sort of to finish up, and that is one related to simply embedded subgraphs. Okay, so it turns out that if we have subgraphs of a larger network that are simply embedded in the sense that neurons outside the graph treat everyone in the graph in the same way, then we get additional structure that allows us to sort of glue together fixed points of subnetworks in order to get the fixed points of the large network. So the big question here, right, is how do you relate fixed points of smaller networks or smaller graphical motifs to the dynamics of a larger network. And this is of great interest in neuroscience because we have all kinds of, there are these ideas of cortical columns and like repeated circuits that are appearing many times and kind of glued together into larger networks in the brain. So we're trying to study this in kind of this toy model. And so one example of that kind of structure comes from what we call the cyclic union. So in a cyclic union, we have subgraphs with nodes, subsets of neurons, tau 1, tau 2, tau 3, and so on. Each of these subgraphs, I'm not showing the edges inside these gray blobs, but you can imagine there's an arbitrary graph there. There's a graph G sub tau 1, a graph G sub tau 2, and it can in principle be any graph you like. But they are strung together in this particular way where all the edges from tau 1, all the neurons from tau 1 have an edge to all the neurons in tau 2, and so on. And so this construction is called a cyclic union, and it is one of many constructions that guarantees that these subgraphs will be simply embedded in the larger network. Okay, so this guarantees a nice embedding of these graphs in the larger network. And what we find, the theorem that we can prove in cases like this, which I think is rather remarkable, is that all the fixed points of the larger network are all obtained by gluing together fixed points of the subnetworks. In other words, any sigma in FP of G, so that is a support of a fixed point for the full network, the full graph, is obtained as a union of sigma i's for FP of G's. So this sigma I, by the way, is a sigma intersect tau I. I should have said that maybe. And so what to remember here is that you have this sort of perfect gluing property. All the fixed points of the large network are obtained from picking one fixed point from each of the subnetworks and gluing it together. And this is an illustration of that rule. So you can have a bunch of component graphs, tau 1, tau 2, tau 3. They need not be small. I'm just showing small ones for illustration. And each of these component graphs has some set of fixed point supports. So for instance, this click 1, 2, there's a single fixed point supported on 1, 2. This graph, 3, 4, 5, has 3 fixed points associated to it that I can also work out with using graph rules and so on. And then when I put them together in a cyclic union here on the right, I can infer from that theorem all the fixed points of the larger graph. They really come from gluing together fixed points, picking one from each of these sets and finding all the combinations. So there are 3 of them. Okay, so this leads us to another elementary graph rule, which has to do with the simply embedded graphs, subgraphs. And so when we have that simply embedded structure, we have, this is sort of the main one, this pairwise gluing rule, where we can sort of infer what are the fixed points for the graph that's obtained by taking the union of those supports. And then you can continue gluing and get the larger network. The cyclic union actually requires this rule C, which is sort of a straight shot from the subgraphs to the larger network. So the point is that these gluing rules for these simply embedded structures are actually giving us kind of like a pre-sheaf and in some cases a sheaf structure, where you can think of picking fixed points from the subnetworks as taking sections of the different subsets and then gluing them together to get a global section, which would be a fixed point of the larger network. So this is something we're very excited about because it gives us a really clean way of connecting the structure of the subnetworks to the structure of the larger network. So this is another, I guess, more careful statement of that cyclic union gluing rule. So I want to, okay, and this is another illustration. So I want to end by giving you a nice example, okay, of using this to actually model something that's sort of in neuroscience, okay? So, and this is this is an application with quadruped gates, okay? So if you have a horse, for example, that horse has many gaits. It can walk, trot, gallop, pace. Pronk is actually not a gait that the horse does, but we threw it in for fun because we could also include it. But the basic idea is you want to design a central pattern generator network that encodes multiple gaits. Okay, so What I'm showing down here is a recent paper, not by us, by other groups, engineers that tried to engineer some network that has different gates. They used coupled oscillator models, which are popular for central pattern generator circuits, and they were able to get 3 different gates in the same network. However, they must change parameters to go from one gate to the other. Okay, and this is the typical situation. Like if you look for models of these central pattern generator circuits, the typical situation is that, okay, sometimes people can encode multiple gates in the same network, but they have to kind of change parameters. So it's not really the same network. It's sort of like they need to make some alteration in order to get the other gate. But the challenge that I sort of posed to Juliana Londono Alvarez, my grad student, is can you use the CTLNs, right, our very simple CTLN networks, and design a single central pattern generator circuit that would encode, all 3 of these and maybe more gates, okay? So the basic idea is you want to have neurons that are representing the legs, so left front, left back, and right back. So we color these. These are the important neurons that are going to determine the structure of the gate. And then you have auxiliary neurons that are sort of there to implement the appropriate dynamics. Okay, so the bound gate, you want nodes 2 and 3 to hit the ground. You want those legs to hit the ground at the same time, so those neurons are firing at the same time, 2 and 3, and then 1 and 4 are firing later. So you kind of have, sometimes I try to show with my own hands and feet, which is kind of not really helpful. So maybe it's good that I can't do that here. But the point is you have these different patterns. Maybe it's more clear here, where you see the bound gate, right? The hind legs go together and the front legs go together, and you get this pattern of activity. So she was able to mimic that bound gate quite easily, and she did it using a cyclic union construction. So this cyclic union that I just showed you, this is exactly what's happening here. You have 4 components. 2 of them involve single neurons, and the other 2 are sort of these larger components of cliques involving the legs. And by putting them together in a cyclic union like this, she was able to easily reproduce the bound gate, and you can see inside the pink rectangle that's focusing in on the neurons that are relevant to determining what gate you're in. And here are the rate curves for the activity. Okay. And then she also went to the other ones. So pace, now she needed to group the left legs together and the right legs together and make a different cyclic union. But again, she could get this sort of checkerboard pattern that gives you pace, just like the engineers in that paper did. Trot is a little different. Now it's like opposite legs. So the left back and the right front go together, and the left front and the right back go together. Again, this looks a little more complicated because she tried to keep the neurons in the same position in her picture, but this is also a cyclic union, exactly like the other ones in terms of its overall structure. And then finally, walk. Here, all 4 legs are hitting the ground at different times. So this is now has to fire in a sequence of length 4. So she was able to get that as well. And then finally, pronk. So pronk is the one that the horses don't do. It's where all 4 legs go up and down together. So I think there are bugs that kind of do pronk, but it's actually not natural in horses. But we threw it in anyway. So that one was also quite easy to do, also with the cyclic union. So with all of these, so she was able to get all of these gates in isolation with the cyclic unions. And now the question is, can you get them all in the same network coexisting? Okay. So the first thing I kind of encouraged her to do, although we were all skeptical that it would work, is simply to just take the union of all these graphs. So in other words, there are, the 4 nodes that are belonging to all the gates, 1, 2, 3, and 4. And then there are these auxiliary neurons, and you can really just take the union of all the graphs in the sense that you keep the edges, all the edges that are there, and now you have a super graph that is like the stupidest rule of just gluing them all together, okay? And just for complete transparency, this union graph is, the adjacency matrix is given right here. All the information that you would need to reproduce the results I'm going to show you are on this slide. So here's the adjacency matrix for that union graph. Here are the epsilon and delta parameters we chose. These are our defaults, in fact. We needed no fine-tuning of those parameters. And you end up with 24 nodes. And of course, we have the usual threshold linear equations. So this is a CTLN with 24 nodes and this choice of epsilon and delta. And the wonderful thing is that, okay, so like I was showing you, she made all those gates in isolation, then kind of glued all the networks together into one super network. Here's all the data. Yeah, you can code it yourself if you want from this slide. And here's the remarkable thing. The super network kept all of the individual gates. Like they're all still there. And so there's something really remarkably modular and robust about these kinds of cyclic union limit cycles, where you can really kind of put them all together, highly overlapping, right? The same 4 neurons are involved in all of them and must go in different order in all of these gates, and yet I can have the coexistence of all 5 of these attractors, of these dynamic attractors, in the exact same network. Okay. So the only difference of whether you're in one or the other is with initial conditions. And moreover, you can actually rapidly switch from one gate to another simply by kicking one of the neurons that's involved sort of uniquely to one gate. So for example, here's a simulation. This is one simulation. So I've started off in the bound gate, and then after some time, I increase the theta variable, the theta input, for only neuron 15. So neuron 15 is actually a neuron that's involved in pace only. So you see it up here. So it's unique to that gate. So if I kick that neuron, I transition into the pace gate. And you can see the transition here. You see the change of the neurons that are firing. Then if I kick neuron 19 sometime later, I can transition to walk. I can also transition to pronk and trot and so on. And these transitions are extremely rapid. You really just like kicking one neuron and you go into the different gates. So not only are these like very robustly encoded in the network, but you can have rapid switching between them with a very sort of limited and simple signal to the network. And so this to me is a really nice illustration of how you can have attractors that are sort of very robustly encoded, but also rapid switching between them, and without any changes of the network parameters. So the W matrix does not change. Nothing changes. The epsilon, the delta, nothing is changing to be able to transition between these different gates. They really just coexist, and rapid switching is possible between them. And I really do have all the gates. If I add noise to the W matrix, I preserve all the gates, but sometimes the transitions fail. So there is some effect. Small amount of noise to the matrix, I actually preserve all the gates and all the transitions. Larger noise, 5% down here, and now I have some transition failures. So, it will break once you jitter it enough, but this is not dependent on like fine tuning of the W matrix. So even though we created this with a CTLN where there are only 2 weights, the -1 plus epsilon and the -1 minus delta, in fact, you can actually perturb those quite a bit, keep the gates, and even keep the smooth transitions between them. So I'm gonna, in the interest of time, this is another story that I will skip. But conclusion, we have, all the fixed points matter, including the unstable ones. We have networks where the graph structure is heavily constraining the allowed dynamics in a way that is understandable with graph rules, and we can use this. We can now use the theory and the intuition to engineer networks that have that perform meaningful computations, like the central pattern generator circuits. And I do want to make a little bit of time just at the end here to advertise this ICIM semester. So this has been approved for us for fall 2023. So for those of you who are interested in neuroscience and math, we are actually going to have a full semester long program, math plus neuroscience, so here's the organizing committee. And the idea of the semester is to bring together theoretical and computational neuroscientists and some experimentalists who will come in as guest speakers and so on, but really to sort of establish stronger connections between theoretical neuroscientists and mathematicians to identify and work on math problems that would help advance neuroscience or theoretical neuroscience as a field. So please stay tuned to that, or drop me an email if you're interested in participating. We're just now starting to advertise, and we haven't sent out invitations for workshops or anything yet. So we're still in the planning phases, but this is coming, and I hope you keep it on your radar. So And with that, I'll just go back to my thank you slide, thank my collaborators and students, and thank you for your attention and your patience with my crashing PowerPoint presentation. And now I'm done. Thank you.
I was saying that if you have a question for Carina, please unmute yourself and ask your question.
I don't see the chat or anything. I don't see anything, just so you know.
No, the chat says thanks.
Okay.
Well, I just got a question. It's about the construction that you made for building this graph, taking the union of it for neural neural networks. Yeah. Well, there were 5 of them. So could you try to use the neural network that was found by the other authors, like the one that the engineers found?
Yeah, that one was completely different because it was based on a coupled oscillator model. So yeah, we really just started over.
Okay.
Yeah, we didn't actually use their construction at all. It was very much a fundamentally different kind of model. So
Oh, it was a different model. Okay.
yeah,
I see now.
It was coupled oscillators, whereas our neurons are not intrinsically oscillating.
Okay. So, and when you take the union, you are just taking the union. Well, so you are using the same 4 neurons on the 5 graphs, and you consider the rest of them different neurons.
No, actually there are 8 that are the same. There are 12 that are the same on all the graphs. So this, I didn't emphasize this before, but you see this one on the left? This core of the super network, these neurons are, well, I should say, there are more repetitions than just the 4. So the 4 are definitely in all the graphs, but for instance, neuron 7 appears in 1, 2, 3, 4 of the gates.
And how do you decide which networks are going to be repeated on the different networks?
So we definitely had to repeat the 4 for the legs, right? Yeah. And then we sort of so we did like play with it a little bit, right? To to keep the gates separated. So we did actually decide on this construction, basically this sort of rectangle of clicks, that this was helpful to make the whole thing more robust once we glued it together. Yeah. Okay. So we did like play a little bit with the architecture so that there would be robustness when we included them.
Okay. Well, thank you very much.
Oh, this is it's not unrelated, but which software do you use to simulate your networks?
Oh, just MATLAB. Yeah, MATLAB and Python. So I should say my current postdoc will not use MATLAB. So she only uses Python. But this was all done in MATLAB.
Thank you. Any more questions for Carina? Okay, otherwise we thank you very much again for your really nice talk. And now you can hear me.
Thank you.